Well, hello and welcome back to the Antiques Roadshow, and today I have a really special piece of history here. What I have here is an iPad, and what makes it particularly special, or rather sort of crap, is that it is the first generation, one of only 15 million sold. I mean really, what are the chances of finding one of these? Anyway, the family and I used this one for about 5 years before upgrading, and despite one or two light marks, it has held up really well, especially the aluminium body. And the reason why it and most Apple products seem to hold up quite well is because they use a lot of anodized aluminium. And the same thing goes for these brake and clutch levers, although these ones have been anodized and dyed. And this chain sprocket, which has been given an extra thick layer of hard coat. Now of course painted aluminium is also very common and it's usually a great deal cheaper than anodizing and a lot easier to do, but if surface finish needs to be durable, it'll be anodized. I mean, paint is okay, but it does scratch easily. And despite aluminium not winning any awards for how scratch resistant a material is, because generally it is quite soft, once it gets anodized, it really becomes something else. That being anodized aluminium. The point is, it's incredibly hard and it wears quite well. Despite how useful it is though, it's not really something I've touched on before, mostly because I use so little aluminium these days, and the parts I do make from it don't really need to be anodized. However, I have a small project in the works where I'll be making a follow focus ring for a few of my lenses, and although the project is not too complicated, it's just a few gears connecting a knob to the lens focusing ring, which will help me pull focus manually. I like to anodize it a dark blue or a black. I think a coat of paint would be too much for these small module gears that I'm using, and in any event, the anodizing should hold up a lot better. Which is exactly why I'm going to use it. And my goal with this video is just to show you that a very basic, or at least an aesthetic anodize, does not need to be too complicated or expensive, with a total cost of less than 50 Australian dollars all in. With that said though, if you can get by without anodizing, I'd probably recommend that. Solely because it can take a lot of time and prep and it doesn't always go right the first time round, and frankly most projects don't need it. But if you do want to do it, I can hopefully show you that a very basic anodize on small parts shouldn't be too difficult or too expensive. First of all though, it is worth understanding what anodizing is. And in its most basic sense, it's a process where we use an electrical current in an electrolyte solution to build up a hard, protective oxide layer around a part. Now of course on its own, aluminium will naturally form its own protective oxide layer, but this is typically only a few nanometers thick, whereas with anodizing, we can form coatings that are easily 25 to 100 microns thick, and that is easily 3 or 4 orders of magnitude thicker. I'm not saying that it's not good enough, but if you want increased resistance to corrosion, increased surface hardness, or adding colour to the part, it will need to be anodized, and the increase in hardness is really nothing to scoff at. Anodized hardcoat, which we found on the sprocket, can easily be 0.1mm thick and reach upwards of 60 to 65 Rockwell C in hardness, which is knife level of hardness. According to the hardness testing files, these were easily 55 Rockwell C hardness and just about 60, which is crazy hard and scratch resistant. Although because it is very brittle and the layer is so thin, if you push down hard enough, you will cause it to crack and you can even hear it cracking. With that said though, this level of hardness shouldn't be too difficult to believe, given that sandblasting garnet and abrasive paper usually use abrasives made from aluminium oxide, and ruby and sapphire are also made from aluminium oxide and they're easily 9 on the Mohs scale. And that's exactly why this racing sprocket is made the way that it is. Aluminium is very light, but also very soft, so you put a hard coat layer on the outside, and that gives you a gear which is incredibly light, but also wear resistant enough to last a few races, which in the world of competitive racing is more than acceptable. With that said though, you can see what happens when the hard coat finally chips away. The underlying aluminium is still soft and it very quickly wears away. But obviously this is sort of worst example. On something like an iPad or an iPhone, you're not going to be putting it under the same sort of loads, and still all these years later, the iPad looks almost good as new. With that said though, don't expect this level of anodizing from a basic home setup. What you need here is a much tighter control of temperatures and current, more so than what I should be able to achieve here. But what I'm really after is that change in colour. And for very simple parts, doing this should not have to be too complicated or too expensive. Of course though, as the size and complexity of your parts grows, so will the process of anodizing, but for small basic parts, you should be able to get it done for easily under $50. And in this video, I'll be anodizing some gears, which will be practice for the focus ring gears, which I'll eventually be making. Before starting though, it is worth knowing what sort of aluminium you are going to be using, because not all alloys of aluminium will anodize equally or the same. The gears that I have here are made from 5000 series aluminium, which are generally well suited for this. Not the nicest alloy to machine, but generally they're going to be fine for anodizing. And the same thing goes for most 5, 6 and 7000 series alloys. But it is always worth checking up because there are some exceptions and tricky alloys. Unfortunately though, a lot of the 2, 3 and 4000 series alloys will have trouble anodizing, or you will pick up off-coloured hues due to the presence of copper. 2011 can especially be troublesome, which is a real shame because it's my preferred alloy to machine and it has poor corrosion resistance. So at least for this alloy, I'll have to stick with etch primer and paint. Parts that are also made from cast aluminium also will have trouble anodizing due to the porous nature of the casting, which will affect the growth of the oxide layer. And it's also worth saying that if you intend your part to get hot, or say do a lot of heat cycles hotter than 80 degrees Celsius, it may be worth looking into other materials, alloys or methods. And the reason for this is that the underlying aluminium expands at about 5 times the rate as the aluminium oxide, and when it heats up too much, it generally results in the anodizing cracking. With that said though, the thinner the coating, the more resistant it will be to cracking. And whilst this probably isn't too important for an aesthetic anodize, it is worth breaking all sharp edges on your part if you can. As we'll cover in a minute, anodizing grows both outwards and inwards, which works fine on flat surfaces, but it will lead to a much thinner coat at a sharp edge. And you can easily see this with the sprocket. The file has trouble biting into it until it reaches the sharp corner where the anodizing is thinner, and at that point it easily bites in. And to also add to that, because the layer grows outwards as well as inwards, the dimension of your part will change very slightly too. On a coat like this, we're probably aiming to get maybe 25 microns at the most, and if we were to measure that on the part, it would show up as a growth of about 12.5 microns in each direction. So essentially the part grows by half the oxide layer in thickness in each direction. And of course on a part, you'd have to account for the growth on each side. And I say this because depending on what your part is, you may have to design the part to be a little bit smaller to account for the growth of that anodized coating. At most, what I'm expecting here is about 25 microns of growth, which really shouldn't matter for most parts. But it is worth thinking about. Next, let's talk about what you need to do this. Again, this is a very basic setup, and depending on your needs, you may need an extra piece or two, but this setup has worked really well for me, and when I won't be needing it, it all stores in this small container. Note that I won't be doing this in the same place where I keep the lathes and the mill. I don't want to do it around them, and I want the garage door and the door behind it to be open for good ventilation. So the first thing you'll need are some containers. These are polypropylene, they're resistant to most acids and bases and solvents, and they're about $3 a piece. They're not very big, but scale this depending on your setup. I've seen people use much bigger setups, and I've seen people use smaller setups than this and still get away with really good finishes. The next thing you'll need is some wire for connecting the anode and the cathode to your power supply. If you're not planning on doing a whole lot of this, aluminium craft wire or aluminium TIG rods are the way to go. They're cheap, they're easy to bend, and you can pick them up from pretty much any hardware store. The only problem that I've found is that they slowly get used up and anodized, which means they need to be stripped of their coating before they can be reused. Although the process for this is quite simple. You soak it in some sodium hydroxide for a minute or two, and then you give it a 2-second sanding. Now the alternative to that is to use some titanium wire, which you don't have to strip afterwards and you can just keep on reusing. It's a bit more expensive, but it is worth it if you plan on doing this a lot. And it's also worth saying, but you shouldn't be using steel or copper wire here. Now the next thing you'll need is a good amount of distilled or demineralized water. A big part of this is keeping the parts clean and the baths free of contamination, and you'll need distilled water for that. Tap water just contains way too many unknown dissolved minerals. And even if you're doing a small amount of anodizing, it is worth picking up at least 2 big containers of it. You know, this stuff is about $1 a litre, so it's not very expensive, but you do use it quite a lot. And once it starts to get contaminated and dirty, you don't really want to use it again. Now the first chemical we need is going to be caustic soda, sodium hydroxide, or lye. Technically, some people do skip this step, but I do think it's worthwhile because it helps remove any fresh aluminium oxide that is formed on the part, post cleaning and sanding, and it also helps to remove any oils that are left on the part. Now some people don't like using it because it can reduce the shine or polish that you give to a part, but in my experience it is worth using it, and a small container like this should be less than $5. The next thing that we need is our acid electrolyte. One of the reasons why I'm making this video is the traditional and commercial electrolyte that would normally be used would be sulfuric acid, or battery acid. Now most guides on the internet will tell you to pick up sulfuric acid, usually from an auto parts or a battery store. But the unfortunate reality is that obtaining it in small quantities here in Australia is quite difficult. Given that most batteries these days are sealed, most battery shops don't seem to stock it anymore, and most drain cleaners that used to use sulfuric acid have seemingly been phased out and replaced by either caustic soda or an enzyme-based solution. Which is a real shame because the last time that I did anodizing, those were my go-to sources for finding dilute sulfuric acid. Now of course, I'm not saying that it's impossible to get. Pool and concrete shops still stock it and it's quite inexpensive, but they usually stock it in only 15 or 20 litre jugs, which is really a bit overkill. The last thing that I want is a 15 litre jug of 32% sulfuric acid just stored away in the garage. You can also get lab grade sulfuric acid in small quantities, but really the price just isn't worth it. Thankfully, the acid salt of sulfuric acid can be readily bought in small quantities. What I have here are sodium bisulphate crystals, and you can pick them up at pretty much any hardware store. And there is some information out there suggesting that this is a suitable alternative to sulfuric acid. Although the amount of information that I could find on the topic was somewhat limited, and what I could find was also conflicting, with some people reporting success, whereas other people were saying that the results just weren't very good or flat out not working at all. So the goal with this video is to see if it works, and if it does, just how well does it work. I hope that it does work though, because it's relatively inexpensive and very easy to obtain. Now there are cheaper bulk options, but this 700 gram bottle was about $10. And for this small setup, that is more than enough. And because we are dealing with an acid, I also have a safe base of bicarb soda just off camera to neutralise it in case of any large spills. The only downside that I've found with it so far is that it does tend to lose its low pH after a while, and then at that point it will need replacing. The same thing will apply to sulfuric acid, but that won't happen as quickly. Now the final purchase that I needed, and this is also optional, is a dye. Unlike titanium anodizing, where the colour is controlled by the oxide thickness, aluminium needs to be dyed a colour. Now the way that it works with aluminium is that the oxide layer that we're growing is porous, which allows the dye to be soaked up into the pores, sealed and then retained. Now there are various professional dyes out there that are intended for this application, but a common DIY choice is RIT fabric dye. I've read that some colours seem to work a lot better than others, with RIT black having a lot more trouble soaking into the part, but from what I've heard, the RIT blue colours seem to have a very good track record. The total cost for it was about $14, which is a bit more than I remember it costing once upon a time, but in the end, $14 isn't a whole lot, and this stuff will last for a very long time. You really don't need a whole lot of it. Just be aware though that some dyes may also need salt to be added to help with colour uniformity and take up, but RIT already has salt added, so that is one thing that I won't have to do. And to finish off, you'll also need a power supply, and controversially, like every time I do something like this, I'm going to use my probably 30-year-old DC power supply. As far as power supplies go, it is about as basic as they come. You can choose between 6 or 12 volts, and that is about it. And unfortunately, this is a bit of a problem because generally with anodizing, we want to be able to control the current, not the voltage. And the reason for that is because when we calculate the oxide thickness, we use something called the 720 rule, which essentially states that it takes 720 amp minutes of current per square foot of surface area to create 1/1000th of an inch of oxide. And for those of us who use metric, there's also the 312 rule, where essentially the anodizing time is the microns thick of coating that you want, times 3.12, divided by the amps, divided by the square meters of the part, I believe. In any event, we generally want to have good control of the current, and we also want to know roughly the surface area of the part that we need to anodize. So usually it's worth having a CAD model of your part handy because the CAD can always calculate it for you. With that said though, that's generally only important if you need to get a specific thickness of anodizing, which I'm not too worried about here because I'm mostly doing this for colour. With that said though, it is pretty useful to know how long you should be anodizing for. And the reason for that is you want at least 12 microns for adequate dye retention, and for really deep colours and better uniformity, 25 microns is really what we're aiming for. And I figure that you can work backwards using a 720 rule calculator, and that roughly does work. Although with all that said, I've generally found with this very basic setup, there is an upper limit to how thick the anodizing coating can be. Because as the anodizing layer grows, the electrical resistance increases and the current drops. And eventually it'll drop to near zero. And it really shouldn't be a huge surprise because here we're using 12 volts, whereas according to the 720 rule calculator, I'd probably be using closer to 16 or 17 for a part this size. And when we're doing hard coat, which is a really thick oxide layer, we're using probably closer to 30 volts. And the higher voltages can work its way through that thicker oxide layer. So I found that when it drops close to zero and there's almost no bubbles being formed, that is usually when I take the part out. And that's usually enough to uptake colour and also impede a bit of hardness and wear resistance. So with all that now said, let's start on actually getting this done. And the first thing that we need to do is make our solution of sodium hydroxide and demineralized water. I've seen a few figures thrown around, but roughly 2% by weight works just fine. A little bit higher is also just fine, but it will be a bit more aggressive and you'll have to take out the part a lot quicker. I also tend to keep this volume of solution to be quite small, just enough to submerge the part and get it clean. It will eventually get contaminated and I prefer to replace it often and in small amounts. In the second container, we'll mix up our Bi-Sulphate solution. Again, I've seen several ranges used, but most fall around the 20% range, which is what I used here. I will, however, be making a larger amount here because the anodizing process does produce a fair amount of heat, and with the smaller volume of liquid that I was using before, I found that it was very difficult to keep that solution in the correct temperature range. For standard anodizing, you want to be able to keep the solution around 20 degrees, and if possible, you want to be able to keep it below 25. And that is also what the large container is used for. I'll fill it up with room temperature water, and that will help draw away heat from the acid solution. Now, of course, there are other ways of doing this. I know a lot of people simply prefer to make a large vat of acid, but at least for me, I'd much rather keep the amount of acid that I need to make to a minimum. And finally, let's talk about our third container off to the side. This is our rinse and waste container. Like every other type of plating or bluing process that we've done, the surface needs to be completely free of grease and oil and any other contaminants. With plating and bluing, getting the surface maybe 99% of the way was acceptable, at least for rust-resistant coatings. But with anodizing, even the smallest amount of oil or contaminants left will be clearly visible once the dye is added. And getting the part completely clean will use up a ton of distilled water. Now, I know that a lot of people prefer to use a big rinsing tank, but I found that using a spray bottle gets the part cleaner and uses the distilled water a lot more effectively. The next thing that I'll do is set up the cathodes. If you plan on doing this a lot, lead sheets with any paint stripped off will work the best as a cathode, but if you don't plan on doing this a lot, aluminium will work just fine too. Just remove it from the acid once you are done anodizing and then clean it off. With the lead cathodes, you can leave them submerged and then just leave them at that until the next time you need to start anodizing. And in terms of placement, two symmetrical on each side would be optimal because the current will take the path of least resistance, and if you have one cathode, there will generally be a thicker coat on one side and that can show up. Now, to what degree that you'll be able to see it is a bit overblown in my opinion, but yes, if you do look for it, you can see the side that was closer to the cathode. So generally, I'll set up two cathodes on each side of the part and that will work just fine. Right, so let's get our test pieces now ready. Anodizing, like bluing, won't cover up an imperfect surface finish. So if you're anodizing for looks, like I'm doing here, it's probably a good idea to sand the part to at least 1200 grit or polish it. I sanded these pieces to only 600 grit and it really wasn't enough. And once you're happy with the surface finish, we can really get started. And from here on, gloves only. We don't want any oily fingers leaving marks on the part. The next thing that we need to do is remove any contaminants or oxides. With a very fresh and polished part, you may be able to skip this, But because of all the hard to reach teeth, I am going to do this step. And for this, I simply use Sif or Jif or Barkeeper's Friend, and I use an old toothbrush to get into the hard to reach places and get rid of any contaminants, oils or oxides. With that now done, I'll now get the part wrapped up using aluminium wire. You want the part to be held in pretty tightly because you won't want it to slip during the process. Because if it does, it'll be very difficult, if not impossible, to re-establish contact, owing to the fact that the oxide isn't very conductive. And if that happens, you'll have to restart. And if you can, it is worth spreading out the points of contact to help with even distribution of power. Although don't go too overboard, or at least try to hide the contact points, because the parts that are in contact won't be anodized and will be left bare. And once we're happy with it, we'll then give it its final spray of brake parts cleaner, which is probably the most powerful solvent that I have here. It'll then get a spray of distilled water before being put in the sodium hydroxide bath. And depending on the part size and the concentration, it only needs about 30 seconds there before you can remove it and then give it its final spray of distilled water. If it did its job correctly, it should have removed any solvent and any new oxide that had formed on the part. And because aluminium oxide forms really quickly, we want to get it in the acid bath as quick as possible. So we'll give it one final spray of distilled water and then get it in the acid tank. The aluminium anodes have also spent a bit of time in the sodium hydroxide just to remove any aluminium oxide that's formed. And once we get it all hooked up, we should be able to see bubbles forming at both the cathode and the anode. What we're forming here is hydrogen and oxygen, which are both flammable, hence why we want good extraction. It also forms a very light acid mist, which you also want to be very careful about, and the extraction should help get rid of it. Now, depending on the shape and size of the part, these bubbles that form can cause you issues because the spots where the bubbles form and cling onto won't get anodized. Now, to prevent this, a lot of people use air bubbler systems or magnetic stirrers to help break up the bubbles, but generally speaking, with very basic small parts like this, I haven't had any issues with bubbles clinging to the parts. Your mileage may vary and you may need to install some sort of air system, but for me so far, it hasn't been an issue. And that's about it. If you're not using maths to calculate the time, you can either just let it run for an hour or two, for a small medium part, or you can use the voltage drop, which is normally what I do. And after roughly an hour and a half or 2 hours, I'm happy with the result. And once it's removed, I'll then give it a final spray of distilled water. Now at this point, it is anodized and generally a bit harder than it was before. It's not hard coat level hard, but it is a bit more wear resistant. And at this point, we can now do two things. We can leave it like this and then seal it and leave it this colour, or we can dye it and then seal it. Now the reason why we seal it is that the surface is porous as it is and it is susceptible to corrosion, which is sort of the opposite of what we want. Now there are a few methods of sealing, but the most basic and probably the worst method of sealing is to simply pop it in boiling water anywhere from half an hour to an hour depending on the thickness of the oxide. And essentially what happens during this process is that we form aluminium hydroxide, and that seals up the pores and hopefully prevents corrosion. The downside to this obviously is that we're heating up the whole part, and because the core, which is just regular aluminium, will expand at about 5 times the rate of the anodized coating, the anodized coating can very easily crack. With that said though, generally with these thinner coatings, say less than 30 microns, we should be able to get away with it without causing any major cracking. And once the part is done, it'll look something like that. Pretty much the exact standard grey that you would get on an iPad. I don't have any hardness testing files on hand, but it will certainly be a bit harder and more scratch resistant than it was before. Of course though, what we're really here is for adding the dye, so let's add that. I've mixed up about 1 parts dye to about 10 parts water, and I'm simply going to dunk the parts in the dye. Technically, this should be heated first, but generally I just leave it in there for about 10 minutes and it still does a very good job at sucking up the dye. And once you're happy with the results, you did the exact same sealing process which we did before. Of course though, I managed not to record it, but you get the rough idea. Now the colour once it comes out will be a little bit lighter than it was, but it should roughly be the same. And at this point you can now observe if the anodizing turned out great or has issues and it needs to be redone. And trust me, it took a few goes to get it correct. The most common source of failure is just not getting the part clean enough, and that will usually show up as tide marks on the part. And at that point, it's pretty much back to square one. Put the part in the sodium hydroxide, let it strip off the coating, and then restart from the beginning. Thankfully though, after about 4 or 5 tries, I got a part that I was pretty happy with. There's still certainly room for improvement, but as far as anodizing goes, it's about as good as I've ever gotten it. And for basic parts, which are just for show, this is more than good enough. Honestly, really happy with it, and I'm really happy that I was able to do all this for less than $50 all in, and I didn't have to worry about getting sulfuric acid. The sodium bisulfate seemed to work pretty well without any major issues. Now, is it better than sulfuric acid? Honestly, I don't know, but it did work here, and at least for very basic setups, you should be able to get away with using it, especially if getting small amounts of sulfuric acid is very difficult for you. And that's about it for now. I hope you enjoyed this video, and thank you very much for watching, and I'll see you next week. Take care.